Lesson 4.3, Multiplying and Dividing Rational Expressions. We will not have any graphing in this lesson. However, a lot of what we'll do is similar in our graphing process. When you're asked to simplify a rational expression, what you want to do is factor both the numerator and denominator completely. So we're used to that. Also, anytime we have a variable in the denominator, we're going to state our domain restrictions. From here, the process is different. When we just have one expression, so one big fraction, once you've stated your restrictions, all we need to do is reduce the fraction if possible. Here's our example on the right. Write an expression that is equivalent to x cubed minus 5x squared minus 24x divided by x cubed plus x squared minus 72x. The first thing I want to be very mindful of when we look at this fraction is that you do not want to just cross off matching terms on top and bottom. We cannot do that when there is addition and subtraction. We really do need to follow these basic steps for 1, 2, and 3. So step 1 is to factor completely. In the numerator, we have x cubed minus 5x squared minus 24x. Notice they all have an x in common. If you factor that plain x out, we would get x squared minus 5x minus 24. And now that's quadratic. Let's see if we can split that constant into two numbers that would add to get the b value in the middle. Numbers that go into 24, we could do 1 and 24, we could do 2 and 12, we could do 3 and 8, or we could do 4 and 6. Let's see which pair seems to make sense. If we take the 3 and the 8 and we make the 8 negative, they would add to get negative 5 in the middle, but they'd multiply to get negative 24. So that means we're going to have x times x plus 3 times x minus 8. That's the factored form for n of x. In the denominator, we have x cubed plus x squared minus 72x. So again, we can factor out an x, and we would have x squared plus 1x minus 72. Ooh, this seems a little intense, doesn't it? X squared plus 1x minus 72. All right, let's see what factors go into 72. I know 1 times 72, but that wouldn't get us anywhere near that 1x in the middle. 2 and 36, yeah, not even close. 3, 24, 4 and 18, 5 doesn't go into 72, 6 and 12, we're getting closer. 7 doesn't go into 72. Ooh, but check this out, everybody. 8 times 9 equals 72. And I think we could work with them. Now, if we have the 8 negative again, their sum would be positive 1, but their product would be negative 72. So I'm going to put that in the denominator. We have that common factor of x on the outside. We have x minus 8 times x plus 9. We've factored the denominator completely. Step 2 is to state any restrictions in the domain. If you notice in the denominator, we've got an x minus 8, and an x plus 9. If any of those x values make the denominator equal to 0, then the whole thing is undefined. So if we set x can't equal 0, that takes care of the first one. But if x minus 8, if that parenthesis can't equal 0, then x can't equal positive 8. And if we have x plus 9, but we know that that parenthesis can't equal 0 either, then x also can't equal negative 9. We have 1, 2, 3 restrictions in our domain. That's step 2. Step 3 is probably the most fun step of all. Now we can reduce the fraction if we have the same factor in the numerator and the denominator. Kind of like a hole in the graph from the last lesson. Well, right away, I see we have an x on top and a plain x on the bottom. So we can cancel both of those out. We have x plus 3 on the top, but there's no x plus 3 on the bottom. We have an x minus 8 on top and on bottom. So it looks like all we have left for our final answer is x plus 3 in the numerator and x plus 9 in the denominator. So notice the x's can't cancel and we cannot reduce the 3 and the 9, and it's all because there's addition in both the numerator and the denominator. We also have to include the fact that x can't equal 0, positive 8, or negative 9. Now remember, we have to include all of our restrictions because at any time if the equation is, or the fraction is undefined, then we can't go any further. So this would be our final answer. Let's try another example. It says, what is the simplified form of the rational expression? What is the domain for which the identity between the two expressions is valid? All of these directions essentially mean the same thing that we did up above. But right out of the gate, we have something unique about the numerator. Instead of x squared being first, that x squared is second, and that's going to make things a little tricky for us. So we're going to want to go ahead and flip that right around, okay? So let's see what we get. If we flip that around in the numerator, we would, instead of having 4 minus x squared, we would have negative x squared plus 4. But as is, x squared, or having a negative out in front, isn't super user-friendly. So what I want to do is factor that negative. And then in the parentheses, let's see what's left. If we take the negative out of negative x squared, that becomes positive, and that will make x squared easier to work with for factoring. Then the plus 4 changes to minus 4. In the denominator, the x squared plus 3x minus 10, we're going to leave that as is. X squared plus 3x minus 10. All right, let's go through steps 1 and 2. In step 1, the first thing we want to do is just factor each. In the numerator, we have that negative 1 on the outside, but then we have x squared minus 4. Now this is a perfect square minus another perfect square. We've worked with that before. The difference of two squares would be x plus 2 and x minus 2. And we have that negative that's still out in front. In the denominator, we have x squared plus 3x minus 10. Numbers that go into 10 are really just 1 and 10 or 2 and 5. Would either pair work in some way to get positive 3 when we add and negative 10 when we multiply? I think we can get that to work if we make the 2 negative but keep the 5 positive. So in the denominator we should have x minus 2 times x plus 5. So that's step 1, just factor. In step 2, we're going to state any restriction domains that we have. We have x plus 2 in that first denominator. Can anybody tell me, can you think about what would the domain restriction be? It's not x plus 2, it's x minus 2. If it's x minus 2, that means x can't equal 2, because that would make the denominator 0. And if we have x plus 5, it can't equal negative 5, because that would make the denominator 0 out. And that's all we do for step 2. Again, step 3, kind of the fun step of all of this, try to reduce anything on top and bottom. That plain negative on the outside isn't going to go anywhere, so we'll leave that. The x plus 2 on the top doesn't match, but we do have a match with the x minus 2s. They're the exact same. So for step 3, we still have a negative on top with an x plus 2. So I'm going to leave that x plus 2 in parentheses. In the denominator, parentheses is optional. You can leave it with the x plus 5, or you can just leave the x plus 5 as is. And then we'll include our, I don't know where that went. We'll include our domain restriction. X can't equal positive 2 or negative 5. We include them both. Now we're going to expand and multiply more than one rational function or rational expression to another one. When you have multiplication, most of the rules stay the same. You're going to first factor all of your numerators and all of your denominators, and then state all domain restrictions. So that's all still the same. The nice thing about this is that any numerator can cancel out with any denominator. So if you have more than one rational expression, anything in the top can cancel out with anything on the bottom. With your parts that are left over, you may have several different groups of parentheses. you'll definitely want to leave your answer in factored form. So let's see how this works. We'll start with an easy example. Example 2a. What is the product of 2xy over z and 3x squared over 4yz? Notice in this set of rational expressions, there isn't anything to factor. We only factor when an expression includes addition or subtraction. So in step 1, we're really not doing anything. We have 2xy over z times 3x squared over 4yz. In step 2, we do need to state our restrictions. Notice we have multiple variables, so we have to include anything that would make the denominator equal 0. Notice x is only in the numerator, so x isn't going to be in this part. For z and y, if we have just a plain z, we know that that denominator can't equal 0. And that would actually apply for this z as well, because 0 times 4 times whatever y would equal would stay 0. But notice we have a plain y, and that can't equal 0 either. So those are our two domain restrictions. For step 3, let's see, what could we reduce? I can see that we have a 2 on top and a 4 on the bottom, so we could reduce that 2, because 2 goes into 4 twice. There's an x on top, but no x on the bottom. There's a y on top and a y on the bottom, so those could reduce. And we can reduce those because there's no addition or subtraction. If we multiply straight across, we have x times 3x squared. That would be 3x cubed. In the denominator, we've got z times 2 times z, and that would be 2z squared. I see nothing else that would reduce for this product. So that would be the final answer. But we also have to say that z and y cannot equal 0. So this is what we'd be looking for our final result. All right, everybody, I'm going to put you to the test on this one. What I'd like you to do is factor all 3 of the rational expressions. Once you do so, go ahead and see if you can determine any restrictions in the domain, and then try to reduce. This will actually reduce to a pretty small answer compared to the original problem. Once you think you have it, press play and we'll see how you did. Okay, let's see how you did. I first factored in step 1, stated my restrictions in step 2. Notice quite a bit canceled out in the numerator and denominator. I had x times x left over in the numerator when I canceled everything possible. That left me with x squared. In the denominator, there's still an x plus 1 that didn't cancel out. And there are 3 restrictions in the domain. X can't equal -3, -1, or +2. If you didn't get this answer, pause the video and see if you can find where things just went in a little different direction for you. If you have any questions, definitely ask tomorrow in our Google Meet. All right, there's one more on the back. All right, our last example. What is the product of x plus 2 over x to the 4th minus 16 and x cubed plus 4x squared minus 12x? There should be a question mark after that. All right, to set this one up, let's go ahead and make sure that we're totally in fraction form. Our first fraction obviously is totally fine, so we're good to go there. X to the 4th minus 16. So the product means we're multiplying. We'll put a little dot in the middle. Since x cubed plus 4x squared minus 12x isn't in fraction form, that simply means that it would be over 1. All over 1. All right, let's go through our process. Step 1, we want to factor completely. In our first fraction, x plus 2 is totally fine. But then we've got x to the 4th minus 16. Technically, 16 is a perfect square, and so is x to the 4th. We've done that before. That would be x squared plus 4 and x squared minus 4. When we FOIL them, we'd get x to the 4th, and then the middle terms would cancel, and we'd get minus 16. But then we have to take a look at, well, this is a sum, so that doesn't factor further, but guess what? This one does. X squared is a perfect square, and so is 4. That will factor into x plus 2 and x minus 2. Oh boy. So we have x plus 2 in the numerator over x squared plus 4, which doesn't factor further, and then another x plus 2 and an x minus 2. Wow, that first fraction really got crazy on us. In that second term, or that second rational expression, notice they each have an x in common, so we could factor that out, and that would give us x squared plus 4x minus 12. All right, let's see what we've got here. We want to multiply to get negative 12, so we could do 1 and 12, 2 and 6, or 3 and 4. Now we need to get positive 4 in the middle, so I think we're going to have to work with that 2 and the 6. If we want positive 4 when we add, but negative 12 when we multiply, the 6 has to stay positive, and I think the 2 is going to become negative. So that would be x minus 2, and x plus 6 all over 1. So that's going to be the hardest part, is kind of getting through the factoring phase of these. Step 2, we want to state any restrictions in our domain, but we're only going to state restrictions that are real restrictions. So if we think about the denominators, if we say that x squared plus 4 can't equal 0, we would subtract 4 only to find out that x squared can't equal a negative number. So what that means is that's an imaginary solution. If we took the square root, we'd get plus or minus 2i, and that's an imaginary solution, so we wouldn't have to do any restrictions here. However, for this x plus 2 that is in the numerator and x minus 2, we have to say that x can't equal negative 2 or positive 2. So put a negative there. Oh, hang on. I suppose I could just make the second one negative. That would have fit too, wouldn't it? So we'll say negative 2 and positive 2. And that's for the two real factors that are down below. Step 3, we're going to go ahead and reduce. So if I take, let's see, I'm just going to reduce, I think, from step 1. That'd be easiest. I have x plus 2 on top, and I have an x plus 2 on the bottom. I have a plain x, but I have no other plain x's. I see x minus 2 and x minus 2. And then there's an x plus 6 on top, but nothing that matches on the bottom. What's left over then in the numerator is that plain x and the x plus 6. There we go. And I believe on Savas, you guys, it leaves it in this form. You wouldn't distribute the x in. Yeah, I think that's what they have you do. So leave it in this form. That's going to keep it simple. Or I suppose you could, you'd get x squared plus 6x, but leave it in that form. And then in the denominator, we have x squared plus 4. And that doesn't factor any further. The parentheses optional, but just recognize that we can't cancel out that x squared because it's in the addition. Oh, and last but not least, we have to state our restrictions. X can't equal negative 2 or positive 2. So again, no graphing, sweet. However, factoring, stating restrictions, and then reducing. That's multiplying rational expressions.